Okay. Good evening, everyone. Let me share my screen and please let me know if the screen is visible to you guys or not. Is my screen visible? I don't. My screen. Okay. Okay. So I should share the screen, like share my slide. Mm, Okay. Okay. Whenever if I'm not audible to you guys, please like message it or just let me know. Okay. If I'm not audible. Okay. So good evening, everyone. Today we are here for the uh, second week class. Just a second, give me a minute. Okay. So good evening, everyone. Today we are here for the second week of our tutorial class on the subject selection of nanomaterials for energy harvesting and storage applications. Okay. So as we discussed in our previous class, we discussed about the solar energy, that how to harvest electricity or how to harvest energy from using the sun. Since we discussed that we are actually in the transition phase from the conventional energy resources such as fossil fuels, coal, natural gas, oil, to renewable energy sources, which is actually the need of the hour, as we can clearly see the climatic changes, and moreover these conventional energy sources, they are like depletive. They will be, and they will be exhausted someday. Okay, in the coming times, or in a couple of years or in a couple of decades, they'll be exhausted. So we need to find an alternative energy source which is endless, which has like no limit. Okay, so for that purpose, we discussed in our previous class that there are various renewable energy sources that we can exhaust. If proper technology is there, then there will be like no energy crisis. Okay. So in the last class, we discussed in detail solar energy. So today we will be discussing in detail the hydrogen energy. Okay. So coming on to the introduction. So what is hydrogen? It is, as we all know, it is the first element on the periodic table. It is the simplest and lightest element. Okay, so it is the simplest and lightest element, and it consists of one proton and one electron. Okay, as you can see here, one proton and one electron. So hydrogen, what the problem is that hydrogen, it doesn't occur naturally in the as a gas on the earth. So it is not like it is not available freely on earth. It is always combined with other elements such as in water or various hydrocarbons such as methane, ethane. So hydrogen is present, but it is not freely present. Like you cannot find hydrogen as a gas on the earth. You need to produce, or you need to like do some kind of reaction with already existing materials, already existing elements such as water or hydrocarbons, to produce nascent hydrogen as like as a pure hydrogen gas. Okay, so hydrogen is also found in many, as I told, it is mainly found in various organic compounds such as mainly in fuels, basically like gasoline, natural gas, methanol, propane. So all these hydrocarbon consist of hydrogen. So it gives us a opportunity that if we can in somehow extract this hydrogen out of these hydrocarbons or water, then we can use that hydrogen as as a energy source. We can use that hydrogen as a fuel. Why so? That also we will discuss. Why hydrogen only, and why hydrogen is a good fuel, that we will discuss in detail today. Okay. So it is basically a fuel cell. It is a device which uses hydrogen and oxygen to produce electricity, heat, and water. Okay. So why hydrogen as energy? Mean why to use hydrogen? Because it has the highest energy content per unit of mass of any chemical fuel. It has very highest energy content compared to any other kind of fuel like crude oil or natural gas or methanol. It has energy content even higher than all those fossil fuels we use till now. Okay. So therefore it can be substituted as an energy source to replace all these exhaustible conventional energy sources. Okay, let me see if someone wants to join. So some of the salient features of hydrogen energy: it is easy to produce. We will study in detail various ways of producing hydrogen. So it is easy in production because it is produced from water, and as we know, water is available on Earth in abundance. It is highly flammable, and you can store it by cooling to extremely low temperature. Okay, you have to cool to like minus 253 degrees C to store it in the form of a gas. Okay, the flame speed of hydrogen burning in air is much greater compared to that of natural gas. Okay, and the energy required, and one more important and benefit of hydrogen is that the energy required to for hydrogen combustion is much less compared to the energy required for the combustion of natural gas or like oil, gasoline, etc. Okay. So now production of hydrogen, how? Because pure hydrogen, it does not occur naturally, as I told. It is available on Earth in combined state in other elements. So it takes a substantial amount of energy in its industrial production. Okay, because it is not freely available, so we need to do different kind of processing to extract hydrogen. Okay, so based on source of energy, there are different ways for the production of hydrogen. So these are different some of the ways of hydrogen production which we will be discussing today. So basically, we can extract hydrogen from fossil fuels and biomass. Then thermochemical processes are also there. Then one of the most famous and trending method of producing hydrogen is electrolysis. Basically, electrolysis, water splitting. Why why this is trending? That also we will discuss. Then solar hydrogen production using solar energy, then biological production. So we will be discussing all this in detail today. So coming to this data, we can see the source distribution in total hydrogen production of 500 billion Newton meter cube per year. It is showing the energy distribution, source distribution from where we are getting energy. So here we can see that 48% natural gas, 30% oil, and 18% coal. All these are non-renewable energy sources. Apart from that, 3.9% from water and 0.1% from others. So assume if these all non-renewable energy sources are exhausted one day in the upcoming decades, what is the main source of energy that we are left with? That is these others, 0.1% and water. So we need to do the thinking, and we need to keep on researching new techniques or new technology of how we can shift from these renewable energy non-renewable energy sources to these renewable sources, so that when these non-renewable energy sources are exhausted, you are not in the shortage of energy. Okay, so hydrogen production from firstly we will be discussing this first method, that is the hydrogen production from fossil fuels. Okay, so fossil fuel processing technologies convert hydrogen containing materials. So what are fossil fuels? As we know, it is oil, natural gas, then gasoline. All of them, they are hydrocarbons and they consist of hydrogen. Okay, so Fossil fuel processing, basically you are processing hydrogen along with the hydrocarbon. So hydrogen containing materials derived from fossil fuels such as gasoline, hydrocarbon. So if you process these like gasoline, hydrocarbon, methanol, ethanol, if you can somehow process them into a hydrogen rich gas stream, then we can extract hydrogen from these fossil fuels. Okay, so the fuel processing of methane is the most common commercial hydrogen production technology. Okay, so till now, if the most popular like method of extracting hydrogen from fossil fuel is by processing methane, that is CH4. So as we can see here, four atoms of hydrogen are present along with carbon. So if we can somehow extract this hydrogen from the methane, then we can use that hydrogen as fuel. Okay. So production of hydrogen from fossil fuel, it occurs in three forms, three ways. Okay. That is firstly steam reforming, then partial oxidation, and then autothermal reforming. So this autothermal reforming is basically the combination of the two. Okay. So coming on to what is steam reforming, it is the most widespread and least expensive process for hydrogen production with high efficiency and low operational and production cost. So what happens here? The most frequently used raw material, the raw materials that we use here are the natural gas, then lighter hydrocarbons such as methanol and other oxygenated hydrocarbons. So these what happens in the steam reforming? These hydrocarbons, they are reacted, or they are feeded into a reactor. This hydrocarbon is feeded into a reactor along with steam. As we can see the reaction, this is hydrocarbon and this is the steam, basically H2O. It is fed, both of them are fed into a reactor, and where they undergo reaction and produce carbon monoxide and hydrogen. So different reactions takes place in different amount of hydrocarbon, and then different amount of water vapor reacts to produce carbon dioxide, carbon monoxide, carbon and hydrogen. And further, this carbon, these products from the first reactions, they further react with the steam to produce more hydrogen, and as we can see in the final step here, we get the highest amount of hydrogen. Okay, so the hydrocarbon raw material is mixed with steam. So the hydrocarbon is the raw material, it is mixed with the steam. Here we can see this steam is there, and here this is the feedstock, which is the hydrocarbon. Okay, now you might see. So here we are putting steam and feedstock, that is the hydrocarbon, in the same reactor. Firstly, the steam is like purified, like hydrocarbon is somehow purified before, and after purification, when this steam is added to it, and here steam reforming takes place at high temperature, and then these four reactions takes place in this steam reformer, and we get the process gas out of here, and different shift reactions takes place. That are these shift reactions takes place, and when we get out the and then the from after the steam reforming, the gases that come out, then they are we can separate different gases by scrubbing or by using pressure, like PSAs. Just a second. So during this process, syngas is produced. Syngas, that is a mixture of hydrogen and carbon monoxide, is produced with lower content of carbon dioxide, and the required reaction temperature is achieved by the addition of oxygen or air. So all this steam reforming, it takes place in the presence of oxygen or steam, which helps in further increase of the temperature for the further combustion of the hydrocarbon in the presence of steam for combusting part of the raw material inside the reactor. The cool product is fed to the CO catalytic converter, where this after the product gas comes out after the steam reforming, it is fed to the catalytic converter, where this carbon monoxide is converted to carbon dioxide and hydrogen in the presence of steam. And the catalyst used can be divided into two ways. There are different kind of catalysts also used in this steam reforming. Some are non-precious metals such as nickel, and some are precious metals such as platinum or rhodium. Okay, so after the product gas comes out, these gases are they are separated from each other to get the pure hydrogen, that is 99.99% purity of hydrogen is produced. Okay. Now coming on to the partial oxidation, here this steam reforming is taking place in complete presence of oxygen. Okay. But here partial oxidation, the gasified raw material can be, here the raw material is basically methane or biogas. So partial oxidation, it is a non-catalytic process. In the last procedure, that is the steam reforming, we use catalyst, but here no catalyst will be used. It is a non-catalytic process in which raw material is gasified in the presence of oxygen and possibly steam, but less amount of oxygen, so that partial oxidation takes place. So this raw material methane, it is gasified in the presence of oxygen and steam at a higher temperature, at a temperature range of 1300 to 1500 degrees C and pressure of 3 to 8 megapascal range. This reaction contributes to the maintenance of equilibrium between the individual reactions. So simply here methane reacts with the oxygen to give syngas, that is carbon monoxide and hydrogen. Then further, this is partial oxidation. Then further oxidation, another in excess oxygen, it produces carbon dioxide and hydrogen, and in the presence of steam, it gives carbon dioxide, carbon monoxide, and excess amount of hydrogen. So in all these reactions, you are getting hydrogen, which can be trapped and used as fuel. Okay. The gaseous mixture formed through partial oxidation consists of carbon monoxide, carbon dioxide, hydrogen, water vapor, then hydrogen, and then methane, and small amount of hydrogen sulfide and carbon oxy sulfide. If there is presence of some amount of that sulfur is also present, then these are also present in the gaseous mixture. Okay. The part of the gas is burned to provide, so some part of the gases we only need this hydrogen. So apart from that, all the gas mixture, it is burned to provide enough heat for the endothermic reaction. All these reactions are endothermic reaction. So to provide heat for these endothermic reactions, this remaining part of the gas mixture is burned to provide heat. Okay. Sometimes catalyst can also be used in order to lower the operating temperature, because this temperature is very high. So if suppose your reactant or your raw material, it is temperature sensitive, or then sometimes we can also use catalyst to lower the partial oxidation temperature. Okay. For natural gas conversion, the just a second. My screen visible? Please reply. Arunmay or anyone? My screen is okay. Okay. So then, where we were, the catalyst can be added to the. So if sometimes catalysts are also added, so for natural gas conversion, the catalysts are typically based on. Mean it is not like ki all the time same reactant will be there. So sometimes methane is used, sometimes biogas is used. So depending on the reactant, if sometimes your raw material is temperature sensitive, then you can add catalyst also. So for natural gas conversion, the catalyst typically is used is nickel or rhodium. Okay. Here we can see simply we insert the feed along with the oxygen. Firstly, feed treatment takes place, purification of the feed or some procedure to pre-treat the feed is done. Then it is introduced in a single reactor along with oxygen, where partial oxidation takes place. Then syngas cooling takes place, and different further this gas is taken for the acid gas removal, such as this hydrogen sulfide, then carbon oxysulfide. All these acid gases are removed. Then further this gas is sent to the pressure swing absorption, where the separation of different types of gases is done from the hydrogen, and we get hydrogen here. Okay. Then coming on to the autothermal reforming. So autothermal reforming is a combination of steam reforming and catalytic partial oxidation. Okay. So it is a combination of both. It is done by bringing the two reforming reactions into close thermal contact or placing them in a single catalytic reactor. Okay, so once the reactor is at operating temperature, the fuel, steam, and air are all fed together in the same step. So here, both all the things are fed together. All the like fuel, then steam and air, all they are fed together in the same step, and the reactants ignite and form the ideal product. And after that, the reaction takes place, and we get the ideal product of hydrogen and carbon dioxide. It has been found that on noble metal-based catalysts are used sometimes. ATR generally follows equilibrium concentration in the output gas based on reaction temperature. Okay. So this ATR, it is similar to steam reforming with an additional catalytic partial oxidation step. So these exothermic steps in catalytic partial oxidation are fast, and the resulting heat can be used to sustain. Mean these partial oxidation steps, they are exothermic. This steam reforming, it is endothermic steps. So the steam which is generated in the partial oxidation, it is used to heat the steam reforming steps. Okay. So this is the typical reaction which is used for the autothermal reforming. Here, hydrocarbon, then oxygen, and then steam, they are fed together, in which we get carbon monoxide and hydrogen. Okay. The advantage here is the not requiring external heat. There is no requirement for external heat, since one reaction is exothermic and one is endothermic. So the exothermic is heating, is assisting the endothermic reaction. It is simple and less expensive. Uh, uh, it is simple and less expensive and starts very rapidly. Okay. And the disadvantage is damage of catalyst may take place if you overheat if overheating of the reaction takes place, or due to heat and mass transfer limitations, sometimes catalyst may get damaged. Okay. So we need to take care of that. We need to control the temperature accordingly. So, what is the criteria of selecting catalytic material in hydrogen production from fossil fuels? So, the main criteria is high temperature stability. The temperature stability should be there because some reactions are exothermic, some are endothermic. So, we need to select the catalytic material accordingly. Then, non-reactive to other material in the process. Okay. So, these catalysts should not react with the other materials. Basically, the raw material, which is our fossil fuel, then water, then moisture, then oxygen. It should not react with all those. It should have high surface area. So some of the popular catalysts are nickel, platinum, ruthenium, then palladium, rhodium, etc. Okay. So the advantage of this hydrogen production from fossil fuel, the first advantage is more heat production than biomass. Then fossil fuels, they are cheap. No, but they also have some disadvantage. Not emission free, mean along with the production of hydrogen, there are various other emissions also, such as carbon monoxide, carbon dioxide. They are also emitted along with. So there is carbon footprint is not zero. So that is a disadvantage. Then the cost of natural gas has tripled in recent years. Then we'll have to rely on imports to mean natural gas is not available everywhere. I mean, obviously, you know that all these non-renewable energy sources, they are not available in abundance in everywhere. So we need to rely on imports for getting the raw material. Then natural gas, it is not renewable. That is the simplest disadvantage. Now coming on to the hydrogen production from biomass. So biomass, it is a renewable organic resource, including forest residues, then millwood waste. There is a lot of biomass waste we can find everywhere, like waste from pulp and paper industries, then agricultural crop waste, animal waste, municipal solid waste, and so on. There's a lot of biomass present. So if we use this biomass to produce hydrogen, then that would be like a very good advantage and very good technology. Okay. So this renewable resource can be used to produce hydrogen. It is basically a renewable resource. Mean these biomass will never end. Okay. So this is a renewable resource which can be used to produce hydrogen along with the other byproducts by gasification. Biomass tend to be bulky, to deteriorate over time, and to be difficult to store and handle. So why to not use this biomass which is very difficult to handle and store. So why not to use it for the extraction of energy? So that would be a great alternative, right? So the researchers are developing new technologies to separate and purify hydrogen from the gas stream produced. Biomass, as you know, it produces lots of gases. So along these gases, they consist of methane and different other hydrocarbons as well. So if we could somehow extract the hydrogen present in these hydrocarbon gases produced from biomass, then that would be a very great idea. Okay. So production of hydrogen from biomass has different methods. That is, one is the thermal method and other is the biological method. Okay, so thermal method, it is simply gasification or pyrolysis or advanced gasification, which includes supercritical water gasification or sorbent enhanced gasification. Then biological method, they are simply fermentation or biophotolysis. Okay, which we will this biological methods we will be discussing at the end. Okay. So coming on to the biomass gasification. So what is gasification? As from the name itself, we are gasifying. We are like heating the biomass to produce the gases. Okay. So gasification, it is a process that converts organic or fossil based carbonaceous materials at high temperature. That is at least at a higher temperature greater than 700 degrees C without combustion with a controlled amount of oxygen or steam, and to produce what? Carbon monoxide, hydrogen, and carbon dioxide. The carbon monoxide then reacts with water to form carbon dioxide and more hydrogen via water gas shift reaction. Okay, so here this is the water gas shift reaction like this. It takes place when you react carbon monoxide with water steam, then you can get carbon dioxide and hydrogen. Okay, since we know carbon monoxide is like very poisonous, so it is better to convert that carbon monoxide to carbon dioxide, and moreover along with that it also produces more amount of hydrogen, so it is a like win-win situation. Okay, along with that, some absorbers or special membranes are used which can separate the hydrogen from the other gas streams, from this other gas streams, basically carbon monoxide, carbon dioxide. Okay, so sometimes separators are used, or like pressure sensitive absorption is used, psas are used, then scrubbers are used to separate the mixture of these gases into different gases. Okay, so gas may also contain particulate matter which is removed using cyclones and scrubbers. Okay. Then particulate free gas, it is compressed and catalytically steam reformed to eliminate the tars and higher hydrocarbons. Then after removing the particulate matters, the gas, it is compressed to remove any heavier hydrocarbons if they are present or tar is present. Then we can remove them by catalytically steam reforming. Then it is followed by high and low temperature shift reactions to produce additional hydrogen. Finally, the hydrogen is separated from the other products by pressure swing absorption. So this is the reaction. Biomass is heated with the steam and it produces hydrogen, carbon dioxide, carbon monoxide, methane, and light and heavyweight hydrocarbons and some amount of char. Okay. Now coming on to the next method, that is pyrolysis. Pyrolysis, it is basically gasification which aims to produce gases, whereas pyrolysis, it aims to produce bio-oils and charcoal. Okay. So in pyrolysis, bio-oil and charcoal, here in the gasification only gases are produced, whereas in the case of pyrolysis, bio-oil and charcoal is present, which is further processed to produce hydrogen. Okay, so hydrogen can be produced by reforming the biomass to a liquid-based bio-oil in a process called pyrolysis. Pyrolysis, it is an endothermic thermal decomposition of biomass carried out in an inert atmosphere, typically at a temperature range of 450 to 550 degrees C. Then this bio oil is a liquid which consists of 85% oxygenated organics and 15% water. So the bio oil, it is then steam reformed in the presence of nickel based catalyst at a temperature range of 750 to 850 degrees C, followed by a shift conversion of carbon monoxide to carbon dioxide. So this is the reaction which is taking place. Firstly, pyrolysis takes place where bio oil and char is produced and some amount of gases also. Then this bio oil, it reacts, it is like processed with the steam to produce carbon monoxide and hydrogen, means steam reforming takes place. Then further this syngas, which is carbon monoxide and hydrogen, it is further reacted with the water to produce hydrogen. Okay. So in all the steps, some amount of hydrogen is produced. Okay. Coming on to the advanced gasification, as here we can see this one. Third part is the advanced gasification, which is of two types. We will be discussing it now. Then advanced gasification, it is of two types. Supercritical water gasification, it is a type of biomass gasification where supercritical water at a temperature of 374 degrees C and a pressure of 22.1 megapascal is used as the medium. Okay, as a medium basically for heating as well as it is a medium as well as the raw material. Okay, so the main difference between supercritical water gasification and other thermochemical gasification technique is that it uses basically the main difference is the gasification medium. Okay, so there we are using simple like steam or like water, but here we are using supercritical water or inert, or in the presence of that medium, basically here inert atmosphere is there, we are not using air or steam. Okay, so basically supercritical water is used. That is the main difference. So supercritical water, it has dual role here. It is a reactant also as well as medium in the gasification of biomass. So the added advantage with supercritical water gasification of biomass is its high pressure hydrogen production. So high pressure hydrogen is produced at a high pressure, which like cuts down the energy or energy cost of compressing hydrogen. As I told, that to store hydrogen we need to compress it. Okay, we need to compress it to condense it to a like liquid state. So here this supercritical water gasification, it is already taking place at a higher pressure, so the cost which is required for compression, it is not required here. So that is also a boon here. Around the supercritical point, water has ability to form, and another advantage is at the supercritical point, water has ability to form ions, which helps in the degradation of biomass components. Mean if different components are produced, different like biomass components, that means side products will be formed. Some not mean undesired hydrocarbons will be formed. Those side undesired side products, they are degraded in the presence of ions, which because at supercritical point water has ability to form ions, so these ions, they assist in the degradation of biomass components. So that is also an advantage. Okay, so there are different catalysts which are used in this supercritical water gasification. Different types of catalysts, catalyst A, B, C, or D, and they are classified as here, like nickel, ruthenium, rhodium, palladium, platinum, then nickel on alumina, then ruthenium on alumina, nickel on carbon. Different catalysts are here. So various different types of catalysts are used along with the at high temperature and pressure. Okay. Now coming on to the sorbent enhanced gasification. Another type is a sorbent enhanced gasification. So what happens here? Sorbent here means there is a absorber along with the gases are along with the gasification. The side products, they are absorbed in a absorber. Okay, which we will be discussing now. So there are two main reactants in the process. The first one is gasifier or the first is gasifier. Any carbonaceous fuel is supplied to the reactor to which steam is also being fed. So this carbonaceous fuel like biomass is like fed to the reactor. Here gasifier or absorber, biomass is fed and then steam is fed, and here gasification takes place. Fuel reacts with the steam to produce a gas mixture of hydrogen, carbon monoxide, carbon dioxide, and some other hydrocarbons. Then carbon monoxide reacts with steam to produce additional hydrogen and carbon dioxide as per the water gas shift reaction. So this is the water gas shift reaction where carbon monoxide reacts with the water to produce carbon dioxide and further uh, hydrogen. Along with that, these carbon dioxide are formed. So what to do? The calcium oxide sorbent is there, which is present in the gasifier. This calcium oxide sorbent, which absorbs the carbon dioxide produced by the reforming reaction and gets converted to calcium carbonate as per the reactions. Okay, so this calcium carbonate, calcium oxide sorbent, it absorbs the carbon dioxide, undesired carbon dioxide, and forms the calcium carbonate, which further this calcium carbonate, the heat released during the endothermic carbon and this reaction, the when carbon dioxide gets absorbed on the calcium oxide, this reaction, this is an exothermic reaction. So this the heat produced from this reaction, it is supplied to the endothermic steam gasification of biomass. Okay, hereby so basically using the excess heat to produce heat to the reaction where heat is required. So basically we don't need to provide external heat. Okay, so after some time, when this calcium oxide it gets converted to calcium carbonate, what happens, it is further this calcium carbonate is regenerated by heating, and after regeneration it converts into calcium oxide, and which is further it can be used for the next procedure. Okay, for the next cycle it gets regenerated. The thermal energy for regeneration is supplied either by burning supplemental fuel or uncombusted char that remains in the calcium carbonate residue. Okay, so some amount of char is also there. So for the regeneration is done by heating. So either we can supply external heat for regeneration, or some we can provide heat by burning the uncombusted char, which is present in the calcium carbonate residue. Okay, so the hydrogen produced may also have small impurities such as carbon monoxide and methane and tar, and it is thus further passed through the gas cleaning station consisting of cyclones, filters, and PSAs to produce a clean hydrogen gas, which is further sent for storage. Okay. Now coming on to criteria for selecting catalytic materials in hydrogen production from biomass. The criteria for selecting the catalyst, the first criteria as always is the high temperature stability. Then it should be non-reactive to other materials in the process, and it should be non-corrosive. Okay. So some examples are carbon nanotubes, that is CNTs, nickel, platinum, ruthenium, activated carbon, palladium, alumina, titanium dioxide, then rhodium. Okay. So what is the advantage of producing hydrogen from biomass? So advantage is opportunity to substitute natural gas, coal with low cost producer gas. Okay. So these biomass, it is easily available everywhere. So therefore it is advantageous compared to the hydrogen produced from the fossil fuels. Okay. So lower NOx, carbon monoxide and particulate emission compared to the fossil fuels. Biomass is always and widely available as a renewable source of energy. It is less expensive than fossil fuel. Okay. Excess utilization of wood leads to deforestation. Biomass energy is not as efficient as fossil fuels. Then complex operation because of the need to control the supply of both air and solid fuel. Okay. High amount of ash and dust remains in the gases. Okay. So now coming on to another method, another process of producing water, which is the thermochemical water splitting. Okay. So, what is thermochemical that we will study? So, with increasing concern of the climatic change and energy security, what we need to shift from, we need to find or search clean and renewable energy sources so that, like all these climatic problems and pollution is brought to a stop. So, hydrogen, as I told, it has the highest energy content per unit mass of the chemical fuel. So, along with that, its burning process, it is non-polluting. It does not burning the hydrogen doesn't produce any pollution. So that is also another advantage. So for the another advantage, like why we should shift to the hydrogen as fuel. Okay, just a second. So coming on to thermochemical water splitting. So what is thermochemical water splitting? Then that we will be studying. Basically, thermochemical water splitting uses high temperature from concentrated solar power. So basically, using the temperature from solar power, like for heating purpose, using the solar energy or from waste heat of nuclear powers reactions and chemical reactions to produce hydrogen and water. For example, as we studied in the last class, if suppose this is the solar energy which is falling onto these heliostats or like parabolic dish concentrator, and after this, these are the concentrators. Then these are then the sun rays are taken to the solar receiver, and at the receiver, as we know that it takes a lot of energy. After getting all the solar energy here, the temperature rises, and here water is stored, and this temperature rise from the solar energy is used for the splitting of water into hydrogen and oxygen. Okay, so if we use the energy from heat energy from different power stations or chemical reactions or solar energy, then that procedure is called the thermochemical water splitting. Okay, how does it work? Thermochemical water splitting processes use high temperature heat, that is 500 to 2000 degrees C, to drive a series of chemical reactions that produces hydrogen. Okay, the chemical used in the process are reused within each cycle, creating a closed loop that consumes only water and produces hydrogen and oxygen. Okay, so the various chemicals which are used in the thermochemical water splitting, they are reused. Mean they are mainly reusable, and with each cycle they are used again, so that's why it is creating a closed loop, and it is only using water as fuel and produces hydrogen and oxygen. Okay, so now for example, what is the mechanism of this solar thermochemical cycle? We need to discuss. So this is a scheme of two-step solar thermochemical cycle. Okay, so here MXOY, it is basically a metal oxide, and where M is the metal and where M is the metal, okay, and O is the oxygen. So in the first step, what happens here, as we can see, this is the solar energy falling on the reactor where metal oxide is there. Basically, metal oxide is the it is a two-step solar thermocycle based on metal oxide redox reaction. So basically here, this is a solar reactor where metal oxide is present. We are taking the metal oxide catalyst. So in the first step, what happens? Endothermic solar step. Metal oxide is thermally dissociated. Mean taking the energy from the sun, it gets excited and gets thermally dissociated into metal and lower valence metal oxide and oxygen. Here we can see it gets dissociated into metal and oxygen and produces oxygen. Okay, so from here we can get the oxygen. Further, the concentrated solar radiation is the energy source for the required high temperature process heat. Okay, so this concentrated solar energy, it is basically the energy source for providing the high temperature. Okay, so in the second, what happens is here in the second exothermic non-solar step. So here we take a catalyst which is solar active, basically a semiconductor which can easily take energy from the sun and gets excited and can undergo redox reaction. So this is basically redox active material we take here, which absorbs energy from the sun and gets excited and undergoes redox reaction. And here we take some non-solar material, basically a metal you can take, which is not redox active. Okay, so in this second step, exothermic non-solar step, the metal which we have taken, it reacts with water. Here water is we introduce water, it reacts with water to produce hydrogen. Okay, so from here hydrogen is taken, and after that this metal oxide and produces hydrogen and metal oxide, and this metal oxide is recycled back to the solar reactor for first step. Okay, so the resulting metal oxide is then recycled back to the first step. So as I told, the material, the chemicals which we using in a thermochemical step, they are basically used again and again in the same loop. So the reaction takes place continuously. Only we need to add hydrogen, and we need to, water. We need to provide water, and we need to provide sunlight. Okay. So coming on to a type of thermochemical water splitting. So basically, it is a sulfur iodine thermochemical water splitting. So thermochemical water splitting is a conversion of water into hydrogen and oxygen by a series of thermally driven chemical reactions. Okay, so the SI cycle. What happens here? Here we use sulfuric acid. The sulfuric acid, it decomposes, releasing oxygen and sulfur dioxide, and further this sulfur dioxide, it reacts with the hydrogen iodide to produce further produce sorry, this firstly what happens is sulfuric acid, it is splitted into sulfur dioxide, water, and oxygen, which takes place, this reaction takes place at a higher temperature of more than 800 degrees C. Further, this reactants, they are reacted, this sulfur dioxide and water, it is reacted with iodine at a lower temperature of around less than 120 degrees C. And when it reacts with the iodine, it again produces sulfuric acid and hydrogen iodide, and this hydrogen iodide is further splitted to produce iodine and hydrogen. Okay. So basically, as I told, the chemicals that we are using in our thermochemical splitting, it gets regenerated again for the another cycle. As we can see here, we have started with sulfuric acid. So we have got here sulfuric acid also, then we added iodine, then we get iodine also, and we get hydrogen also. Okay. So basically, all the reactants which we are introducing, they get regenerated at the end of the cycle to use them for the next cycle. With a suitable catalyst, the high temperature decomposition of sulfuric acid achieves 10% conversion at 510 degrees C and 83% conversion at 850 degrees C. So basically, it is showing that the temperature is also very important. If we do the reaction at around 510 degrees C, then the conversion is only 10%. But if we increase it up to 850 degrees C, then you can see how much increase is there. The conversion increases up to 83 degrees C. Okay. So the process is basically the sulfuric acid decomposed, releasing the oxygen and recycling the sulfur dioxide. The hydrogen iodide can be decomposed at about 400 degrees C, releasing hydrogen and recycling the iodine. And the net reaction is the decomposition of water into hydrogen and oxygen. The whole process, it takes place in only water and high temperature heat and releases hydrogen. Okay. And all the heat which is you can see here 800 degrees C, 120, all that heat comes from the sunlight. Okay. And we can see all these reagents, they are recyclable and there is literally no effluent. Okay. So now coming on to different nano materials which are used in hydrogen production for thermochemical reaction. So there are various nanomaterials used, mainly like graphene, then graphene, graphitic carbon nitride, hexagonal boron nitride, black phosphorus, then transition metal dichalcogenides, then nitrogen doped graphene, and other heteroatom doped graphene. So basically, graphene, you might have heard, it is a very famous nanomaterial which is gaining lot of interest right now. It is a very versatile material which is used in mostly every field such as electronics, biomedical engineering, then electrocatalysis, then optical electro optics. It is such a versatile nanomaterial that it is finding application in most applications right now. Okay, so basically, what is graphene? It is basically a one atom thick 2D carbon crystal in which sp2 bonded carbons atoms are packed in a hexagonal lattice resembling a honeycomb. So as you can see, it is resembling a honeycomb, and all these carbon atoms, they are sp2 hybridized carbon atoms which are like packed in a hexagonal lattice, and it is resembling a honeycomb. It is considered as a fundamental building block for another dimensional carbon metal. So it is basically like this is such a versatile material. This graphene, as you might have heard about graphite. So graphene is produced simply. What we do, we take a scotch tape, we just tape it over the graphite, and then we take it off, and that is the graphene. Basically, graphite is multi-layered, whereas graphene is a single layer of the graphite is graphene. Okay, so what happens, suppose for example, this is graphite, lots of layers of I mean this these layers arranged in one over other, so this is graphite. Okay, so if you suppose take a tape and like scotch tape over it, over graphite, and you just put tape over the graphite stone, and then take it off. Over the tape you will see a single layer like this. That single layer, this single layer, if you consider this single layer, this is graphene. Okay. Okay. So basically, a single layer of graphite, it is graphene. And graphene, it is a fundamental building block of various other nanoparticles also. So it is it is a fundamental dimensional block for building block for other carbon materials also, such as fullerene, then 1D carbon nanotubes, then 3D bulky graphite, and other carbon architectures are also can be built using graphene. Okay. So the cause of why this graphene is of so much interest, because it has various unique properties such as high theoretical surface area, that is around 2630 meters square per gram. Then high modulus of elasticity, there good thermal conductivity, good electrical conductivity. So all these property make it such a versatile material that it is used in mostly all the applications right now. Okay. Now coming to another is the graphene. So graphene is simply another allotrope of carbon in which one atom thick plain sheet of and sp2 bonded carbon atoms arranged in a crystal lattice. So this is the sp2 bonded carbon, and these are sp bonded carbons. So two sp2 bonded carbons are linked together using a single sheet of sp. So, depending on how many sp hybridized carbons are there in between two sp2 hybridized benzene rings, you can the name of the nanomaterial changes. So, basically, this is the acetylene chain, and this is graphene. So, joining this acetylene and graphene, we got the name graphene. Okay. So comprised of benzene ring, which is sp2 hybridized, and acetylenic chain, which is sp-like carbon atoms linkers. Graphenes were named after their relationship. Okay, so they are differentiated as graphene, graphtine. Depending on how many carbons are there, hybridized carbon are there between sp2 hybridized ring, the name of the nanomaterial change based on the number of acetylene groups between two adjacent benzene rings. Okay. So the synthesis of 2D graphene is mainly based on bottom-up methods such as chemical vapor deposition, that is CVD, gas liquid or liquid process using hexaethynyl benzene as the precursor monomer. Okay. Another nanoparticle is the graphitic carbon nitride. Why we are discussing these nanoparticles in detail? Because right now we are in the era where nanoparticles are gaining lots of interest, and mostly those nanoparticles, they are carbon based nanoparticles, which are very famous due to their very versatile properties. Therefore we are discussing the some of the widely trending carbon based nanoparticles in detail. Okay, so the carbon nitride is one of the first artificial polymers reported in the scientific literature. Okay, so the graphitic carbon nitride, it is basically C3N4. If suppose we take this one in just a second. Suppose we take this part, if we consider this part, in this we can see 3 carbon and 4 nitrogen. That is the formula here, C3N4. It is a 2D crystal with van der Waals layered structure, and it's considered to be the most stable allotrope among the various carbon nitride materials. Okay. Analogous to graphene, the crystal structure of the C3N4 can be described as hexagonal carbon framework with N substituted carbon through sp2 hybridization of carbon and nitrogen atoms. Two structural isomers of C3N4 exist and are synthesized using different precursors. So different isomers of this graphitic carbon nitrides are present, and they are produced using different precursors and different methods. Okay. Now coming on to another, that is hexagonal boron nitride, which is HBN. It is also called HBN. It is another analog of graphite, and it is known as the white graphene. Okay, so this is the structure, hexagonal boron nitride. So the blue one is the nitrogen, and this one is the boron. Okay, bulk hexagonal boron nitride has a layered structure with lattice constant of 2.50 angstrom and interlayer distance of 3.33 angstrom. So it differs from the graphene, but how it differs from the graphene? It is an insulator with a thickness dependent band gap. In electronic and optical devices, the HBN nanosheets have been used as a dielectric substance for graphene and MOS2 based heterostructures. Okay. So basically pristine HBN, it displays barely no performance for electrocatalysis, limited by its poor conductivity and poor catalytic activity. So the main problem here is it has a like a good structure, but doesn't have like conductivity properties, so it cannot be used as electrocatalyst. So for that purpose, people right now researchers are focusing on modifying this hexagonal boron nitride to improve its conductivity and catalytic activity. Okay. Now another one is a black phosphorus. It has 100 years long history. It is a layered semiconductor with an orthorhombic crystal structure. Okay, it has an orthorhombic crystal structure. One phosphorus atom is covalently bonded with another three to form a puckered honeycomb structure in a single layer, as you can see here. Three bonds take up all three valence electrons of phosphorus, resulting in a band gap of 2 electron volt, which can be tuned by controlling its thickness. So, mean basically you can modulate its band gap also by controlling its thickness. Okay. So only a few works have been reported about its application in electrocatalysts due to its low stability under electrocatalytic condition and poor electrical conductivity. Just a second. Okay. Now coming on to the next one, which is transition metal dichalcogenides, which are TMDs. It can be described the general chemical formula, which is MX2, where M is a transition metal element and X is a chalcogen such as sulfur, selenium, tellurium. Okay, and these are the transition metals. So bulk TMDs, they consist of a monolayer stacked by van der Waals forces, whereas the general crystal structure of a TMD monolayer can be described as a sandwich structure where one layer of transition metal is situated between two layers of chalcogen. So basically, one layer of transition metal M and two layers of chalcogens. So this is the structure basically. Okay. A unique feature of 2D transition metal dichalcogenide is their multi-crystal structure. Okay. So you might have heard like molybdenum disulfide. So, like, it is a famous transition metal dichalcogenides. Okay. Another is the nitrogen doped graphene. Nitrogen doped graphene is the most studied graphene-based electrocatalyst due to its simple synthesis process and relatively good electrocatalytic performance. Nitrogen is of similar atomic size as carbon, but it is more electronegative. Therefore, doping with nitrogen can change the electronic configuration of graphene while minimizing the lattice mismatch after doping. Okay. So basically, here doping with nitrogen is beneficial because it is more electronegative, due to which the more electronegative, as well as the structure, the size of the nitrogen and carbon, they are like comparable. Therefore, doping with it with nitrogen electronic configuration does not mean changes without lattice mismatch. Okay. So, being the earliest studied, the most important and metal-free electrocatalyst for the ORR, nitrogen doped graphene has demonstrated some unique characteristics. Okay, so nitrogen graphene has tolerance to the fuel present in the anode, which largely prevents the crossover. Another advantage with the nitrogen doped graphene is that it has good tolerance to the fuel, like to the biomass and all. They mean if different gases are produced at different cathodes, mean different electrodes, then nitrogen doped graphite, it has good tolerance of with the fuel, that is carbon monoxide and carbon dioxide and methanol. It does not react with the nitrogen doped graphite. Therefore, does not allow it to move to the other electrode, and mixing of hydrogen and different other side gases does not take place. Okay. Hello. Now another is the other heteroatom doped graphene. So there are nowadays people are exploring and experimenting with different heteroatoms, doping graphene with different heteroatoms to see to modify it and to improve its various properties. So beside nitrogen, other p block atoms such as boron, sulfur, then phosphorus have been doped into the graphene by physical or chemical approaches. Similar to nitrogen, the different size and electronegativity of these heteroatoms can also induce electron modulation and change the electronic properties of pristine graphene. These kind of electrocatalysts can usually be prepared by annealing graphene oxide with appropriate heteroatom containing precursor at high temperature. Simply by annealing graphene oxide with these with the precursor of these heteroatom and heating them at room temperature, mean basically annealing them together, can dope graphene with these heteroatoms. So the doping level of these materials is normally lower than that of the nitrogen doped, and doping graphene with heteroatom of either higher or lower electronegativities than carbon can induce electrocatalytic activity through intramolecular charge transfer in graphene matrix. Now coming on to the another method, which is hydrogen production via water electrolysis. Okay. So basically, water electrolysis is currently the most trending procedure of hydrogen production. Why? So that also we will discuss. As the world is generating a lot of pollutants enough to change adversely the ecosystem, there is a need of clean energy. So basically, if we simply use water and apply potential, and if simply we can split water by applying potential, and somehow if the potential that we apply is also coming from a renewable energy source, the energy for that potential is also coming from the renewable energy source, then that would be the most beneficial method to produce hydrogen without producing any external pollutants, or without basically like contributing to harming the environment. Okay. So the hydrogen is not found in appreciable, or as I told, it is not freely available on earth. So basically hydrogen may be produced via electrolysis of water. In this process, Electricity is used to break down the water into components, that is oxygen and hydrogen, with no harmful or polluting side products. Okay. So when a water molecule passes through a electrochemical process, water molecules split into hydrogen and oxygen, and this process is called water electrolysis. Electricity is used for the splitting of hydrogen and oxygen into their gaseous phases. This technique produces clean energy without emission of pollutants by utilizing electricity. So this is a reaction. Liquid, that water is used, we provide potential, and it produces hydrogen and oxygen. Okay. For water electrolysis, the energy is required as electric energy from a DC source. At room temperature, the splitting of water, it is very small. At room temperature, splitting of water is very small. That is approximately 10 to the power minus 7 mole per liter, because pure water is basically very poor conductor of electricity. So if we add some amount of salt or different like acid or base to water, it can improve its conductivity, and further can be, I mean, it makes it a bit easier for the splitting of water. Okay. So therefore, acid or base is used to improve the conductivity. In an alkaline electrolyzer, potassium hydroxide, sodium hydroxide, or like sulfuric acid solutions are used mainly used with the water to improve its conductivity. Okay. The solution split into ions, positive and negative ions, and these ions readily conduct electricity in a water solution by flowing from one electrode to the other. Okay. So, coming on to the classification of water electrolysis technologies, it is of three types: alkaline electrolysis, polymer proton electrolyte membrane based electrolysis, then steam electrolysis. Okay. So, coming on to the alkaline electrolysis, the hydrogen production by alkaline electrolysis is one of the environmental friendly procedures, zero emission of carbon dioxide. If this process combined with renewable energy sources, basically, if the potential applied is also coming from a renewable energy sources, then this is a boon. Okay. The alkaline water electrolysis is the oldest technology. It is the easiest, simplest, and suitable method for hydrogen production. So, alkaline electrolyzer decomposes water and hydrogen, decomposes water and produces hydrogen and oxygen. And the electrolyte is an aqueous solution containing NaOH or KOH with a typical concentration of 20 to 40%, and operating temperatures are basically 343 to 363 Kelvin and a pressure of 3 megapascal. Okay. So simply what happens is the NaOH, it gets dissociated into as soon as here we can see this is this is anode, this is cathode, and if we add like NaOH into the water, basically alkaline, making water alkaline, what happens as we apply the potential, this NaOH will split into Na positive and OH negative. Further, this Na positive will help in the dissociation of water. Basically, it will help in the dissociation of H2O. It will react with the OH part of the H2O, and H positive will go to the will be released from here. Hydrogen will be released from here, and oxygen will be released from here. So the advantage is it is the oldest and well-established technology, long-term durability. This technology is commercialized and running with efficiencies almost 70%. Okay. The electrolyte is liquid and it leads to disadvantages. It may lead to corrosion, low current density, and high energy consumption, because we need to provide the DC source. So it is a high energy consumption procedure. Now coming on to proton membrane electrolysis, basically PEM membrane. So the proton exchange membrane water electrolysis is based on a use of a polymeric proton exchange membrane as a solid electrolyte. So this yellow part, it is a solid electrolyte, basically a membrane, polymer based membrane. Polymer PEM electrolyzers are characterized by the very simple construction and their compactness. When operating in electrolysis, the water decomposes at the anode into proton. Here, proton is produced at the anode. Sorry, it is opposite. The water decomposes at the anode into proton and molecular oxygen. The oxygen is evacuated by the water circulation oxygen evacuates with the water circulation, and proton migrates to the cathode. This proton, it migrates to the cathode. Here, water splitting takes place at the anode, okay? And it splits into H positive and molecular oxygen, which goes from here. And this proton, it shifts to the cathode under the effect of electric field, and they are reduced to molecular oxygen. After getting reduced to molecular oxygen with the electron which is coming from the external circuit, it gets reduced to hydrogen, and molecular hydrogen, it gets away, it is taken out from the cathode side. So advantage here is the high purity of hydrogen gas, lower power consumption, ecological cleanliness, high safety, and easy handling and maintenance. So disadvantage is the cost of the components are high, comparatively low durable, and new and partially established, and commercialization may happen in the future, but right now it is not commercialized. Coming on to the steam electrolysis. Why steam electrolysis? Since I told you that water at room temperature is water splitting at room temperature is very low. So if we increase the temperature, then the splitting will also increase. So therefore, if we firstly convert this water into steam and then we try to split this steam, its efficiency will definitely increase. One of the major problem of conventional electrolyzers is their high electrical consumption. So steam electrolysis that reaches high total energy efficiency compared to alkaline or PEM electrolyzers. So at high temperature, the water vapor is reduced to hydrogen. Ionic conductivity of the electrolyte and rate of the electrochemical reaction at the electrode increases with that temperature, because with the increase in the temperature, different kinetics also increases, electrochemical reaction rate increases, and ionic conductivity of the electrolyte increases. So along with that, along with or taking all these factors into mind, steam electrolysis is much efficient compared to the compared to the alkaline and proton exchange membrane electrolysis. Okay, we can get the high temperature from waste heat of the processes like nuclear origin, then solar, geothermal, fossil, and from any other thermal process. Okay. So advantage here is the high process pressure operation. Advantage is high pressure operation, higher efficiency, almost 100%. We can get high temperature from solar energy, which is a renewable source. But the disadvantage is this technology is still in the laboratory phase, low durability due to high heat, and design of the system is bulky since it is taking place at high temperature. Okay. So basic chemical react. Just okay. So basic chemical reactions on operating temperatures. Am I audible? Okay. The basic chemical reactions and operating temperatures range for different types of water electrolysis are given here. So this is the these three types of electrolysis we studied. So these are the anode reactions at the three types of electrolysis. These are the cathode reactions where hydrogen is evaluated, which is HER, hydrogen evaluation reaction. At the anode, it is oxygen evaluation reaction. Here the charge carrier in the alkaline electrolysis is the OH negative, in membrane electrolysis H positive, and in the case of high temperature electrolysis, it is the O2 negative. And temperature range is like alkaline electrolysis takes place in the range of 40 to 90 degrees C. Then membrane electrolysis takes place in the range of 20 to 100 degrees C. And whereas the steam electrolysis, it takes place at a much higher temperature of 700 to 1000 degrees C. Okay. Now coming on to some of the criteria to choose nanomaterials in electrolysis for hydrogen generation. So to choose electrode material, criteria is high cyclability. Mean electrode material should be as such that it can undergo different cycles of hydrogen production. Mean it should have higher durability basically, like shelf life should be good. Then high ionic conductivity should be there, high surface area should be there, high mechanical and chemical and thermal stability should be there. Then PEM materials, like PEM material, basically the basically the proton exchange membrane material, it should have high ionic conductivity, high oxidative stability, low permeability of gases, electrically insulator it should, and then high. Why electrically insulator? Because basically this membrane, it acts as a separator. So if it will be electrically conducting, then short circuit will be there. Then high surface area should be there. Then high mechanical, chemical, and thermal stability should be there. So normally, right now, initially Nafion was used. Right now, people are using peak, that is polyether ether ketone. Then they are using by sulfonating it also, that is sulfonated polyether ether ketone. And they are still now people are like focusing on various new membranes such as piperidinium based membranes. So people are like researchers are inventing new membranes each day. Okay. Now, criteria for choosing the catalyst material, it should have high thermal stability, then non-reactive with the electrolyte material, it should be non-corrosive, then high surface area should be there. Okay, these are the examples of membranes used in Chem as separator. Okay, now coming on to different materials which are used in electrolysis of hydrogen generation. So these are different materials which are used. You can study here in the alkaline electrolyzers, then PEM electrolyzers, and some solid oxides which are also used as anode materials. These are the cathode materials. These are the electrolyte materials, and these are the catalyst materials. Okay. Now coming on to the other type of hydrogen production, which is from the photochemical processes. So basically, what is photochemical? It is basically simply we are taking a material which the production of hydrogen using solar energy. Basically, using the solar energy, we will be trying to split water to produce hydrogen. Okay. So, hydrogen is widely considered to be the fuel in the powering of non polluting vehicles, domestic heatings, and aircrafts. The abundant supply of water and sunlight offers an affordable alternative source to produce hydrogen apart from fossil fuels and biomass. So, another form is that is the photoelectrochemical water splitting. It is one of the potential technique for clean solar hydrogen production and has been utilized in small to large scale hydrogen generators. Okay, so what is photoelectrochemical water splitting we will be studying? Okay, so it is based on the conversion of light energy into electricity within a cell involving two electrodes immersed in an aqueous electrolyte, of which at least one is made of the semiconductor exposed to light and able to light. Okay, so basically what is the logic behind? Two electrodes are there, out of which one should be semiconductor, basically, which can be exposed to light, and it can absorb light and get excited and produce holes and electrons which will assist in splitting of water. Okay, so the electricity is then used for water. So the production of this hole and electrons from the semiconductor, they helps in the splitting of water, and thus water splitting takes place and hydrogen is generated. Okay, so there are three options for arrangement of photoelectrodes in the assembly of PEC. So two electrodes are there. So suppose one electrode is photoanode, which is made of n-type semiconductor, and cathode is made of metal. Either we take one semiconductor and one metal, then either we can take both the semiconductors, or we can shift the arrangement, that is one p-type semiconductor and another metal, one n-type semiconductor and metal, or both one n-type semiconductor and one is p-type. Okay, so we will be studying further. The simple mechanism here is this photoanode, it when it absorbs sunlight, it gets splitted into electron and holes, and then electron and hole assist in the water splitting. Okay, So let us come to the reaction mechanism. What happens is water photoelectrolysis using a PEC involves several processes within electrodes at the within photoelectrode and at the photoelectrode electrolyte interface. So different reactions takes place. So light induced intrinsic ionization of the semiconducting material results. So suppose this is the photoelectrode. So this photoelectrode, it absorbs sunlight, and on after absorbing sunlight, light induced intrinsic ionization of the semiconducting material, it results in the formation of electronic charge carriers. So this is an electron, and these are two electrons are formed and two holes are formed. Okay, where H is the Planck's constant, nu is the frequency, is the electron, and H positive is the hole. Okay, so now this hole is used for the oxidation of water at the photoanode. Here on the surface of this photoanode, the water uses hole for oxidation and produces oxygen. Okay, so here oxygen is produced at the anode surface, and two protons are produced. So these protons, it shifts towards the cathode, and after here two holes are produced at the anode, and two, as I told, two electrons are also produced. So those electrons, they flow into the external circuit and move towards the cathode, and from here these two protons are moving towards the cathode, and here two cathode and two anode, they combine, and the proton gets reduced to produce elemental hydrogen. Okay, so transport of hydrogen ions from the photoanode to the cathode through the electrolyte, and transport of electrons from the photoanode to the cathode through external circuit takes place, and the reduction of the hydrogen ion at the cathode by electron takes place, producing a uh, elemental hydrogen gas. Okay, so the PC cell structure, it is of different types: single photoelectrode PEC system, biphotoelectrode PEC system, hybrid photoelectrode PEC system, and photoelectrode sensitized through incorporation of particles of noble metals, and photoelectrode sensitized through dye deposition. Okay, so let us discuss one by one. Single photoelectrode PC system is where one photoelectrode is present and other is metal. As here, this is photoelectrode and this is simply a metal. So this can absorb sunlight and gets split into, like, basically this is a semiconductor which absorbs sunlight and gets split into electron and holes, whereas this is a simple metal which does not split into electron and holes. Okay, whereas if sometimes we can use both the electrode as photo electrodes, that is one n type and one p type. Therefore, if when they will absorb sunlight, they will produce photo voltage, mean they will produce electron and holes on both side and will assist in water electrolysis. Okay, now hybrid photoelectrode, which is the structure of a HPV which involves the metal contact. So here in the hybrid photoelectrode, what happens, where there is a metal electrode, then silicon cell is there, which is one layer of p-type silicon cell and another n-type silicon cell, then photoelectrode, then another photoanode which is TiO2, thin layer of TiO2 is there, and aqueous electrolyte is here. So this TiO2 thin layer is only in the contact of liquid electrolyte. In this structure, only TiO2 layer is exposed to the aqueous environment, while the silicon solar cell forms a sublayer that is not in contact with the electrolyte. Okay. So the silicon solar cell, it is used to generate the photovoltage. So here splitting into electron in these two layers, splitting into electron and hole pair takes place, which which can be used as the internal electrical bias. So we do not need to like provide any external power source. Okay, so consequently this type of hybrid photoelectrode is expected to exhibit intrinsic performance in the absence of an external bias. External bias, basically external power. Okay, the electrochemical chain incorporated within the HPE, it is shown here. So what happens? The layer of metal, then N type silicon, P type silicon, then TiO2, and here
water is there. So what happened at the interface of this TiO2 and water? This TiO2 absorbs sunlight and gets split into electron and hole. This hole goes on the surface of this photoanode, and using this hole, water gets oxidized to release nascent oxygen at the anode, and further the proton move towards the cathode side, where electron from the external circuit moves to the this cathode side, and that proton gets reduced and produce atomic hydrogen. Okay, so here no need of external power source. Okay. So photoelectrodes, another is photoelectrodes, electrodes sensitized through incorporation of particles of noble metals. So photoanode may be sensitized, some amount of small particles of noble gases, noble metals such as silver and platinum are sensitized over the photoanodes and form a dispersed system involving, basically forming a composite kind of, basically involving nanoparticles to further increase the efficiency of the photoelectrode. Okay. Another is photoelectrode sensitized through dye deposition. So the conversion efficiency may be increased by dye sensitization of photoelectrode. So what happened? The photosensitizer, photoanode, it is sensitized or coated with, or coated with dye, which is physically attached to the surface of the photoelectrode. So light gets absorbed by the dye, which leads to the transformation of the dye molecules from the ground state to the excited state. So the dye molecules absorbs the sunlight, it gets excited and forms dye prime. And after that, after further absorption of the sunlight, the this dye prime, which is the excited state, it goes to higher oxidation state and forms dye positive, results in the formation of, and after releasing an electron. Consequently, the oxidized dye molecule reacts with water. This oxidized dye molecule, it reacts with water to produce nascent oxygen and proton. And further, this proton gets reduced using the electron, which was released by the oxidation of dye, and it produces nascent hydrogen. Okay. So the dye-sensitized semiconducting photoelectrode exhibits two functions. Firstly, the absorption of light by the dye. Dye absorbs the light and releases an electron, and charge transferred by the semiconductor, where water splitting takes place. Okay. So the dye sensitization will lead to sustainable performance of photoelectrode only when sensitizers exhibit a stable performance in aqueous solutions. Okay. Now coming on to the performance of PECs, it is considered in the terms of excitation of electron hole pair in photoelectrode. How easily the excitation of the photoelectrode takes place and how easily the electrons and hole pairs are forming. Then how easily the charge separation takes place, how easily the electron and holes are separating and helping in the water splitting. Then electrode proceeds and related charge transfer within PECs. Then generation of PEC voltage required for water decomposition. Okay. Now, another is the what is the criteria of choosing material for PC cells? It should the material like photoelectrode, they should have a band gap of 2 electron volt. High optical absorption should be there. High electron mobility should be there. Then stability in strong electrolytes, non-corrosive, and high catalytic properties should be there. So different nanomaterials are used in PECs. Basically, the carbon doped titanium dioxide, nanocrystalline films, titanium dioxide, nanotube arrays, zinc oxide, nanostructures. There are various different nanomaterials are used. Okay. Then another thing is the solar energy conversion efficiency. There is this formula for solar energy conversion efficiency, which is delta G H2O, which is the Gibbs free energy of formation of 1 mole of liquid hydrogen, liquid water. Then RH2, which is the rate of hydrogen generation. V bias is the bias voltage applied to the cell, that is the external bias which is required, external power. Then I is the current within the cell. IR is the incidence of solar irradiance, which depends on geographical location, how easily the sunlight is getting irradiated over the PEC. And then A is the irradiated area. Okay, so this is the formula for
solar energy conversion efficiency. Now, system selection, the search for high performance photoelectrode for solar hydrogen generation includes a wide range of compounds of different composition, structure, microstructure, and electronic structure. So, with the highest conversion efficiency, there are various semiconductors which have a very highest conversion efficiency, that is gallium arsenide, gallium indium phosphate, aluminum gallium arsenide. But these materials are not practical since they are very costly and have poor chemical stability in water. And simply water stability is then, and if they are not stable in water, then there is no need. On the other hand, whereas metal oxides such as titanium dioxide, they exhibit much better stability in water and they are less expensive. Okay. Now coming on to the advantage and disadvantage of PEC. So this technology depends on solar energy, which is a renewable energy source, which is a very good advantage. Then it is environmentally safe with no undesirable products. It may be used on both large and small scales, but disadvantage is also there, which is difficult to get sunlight at all places or like on cloudy weather. Then it may require complicated optical setup. Then device stability should be there, durability should be there, reliability there should be there, robustness. All these are a major challenge for PEC commercialization. Okay. Now coming on to another type, as I told you in the earlier section that we will be discussing the biological type of in like further class in the last section. So this biological methods we will be studying now. So hydrogen is the fuel of the future. As I told, it is due to this high conversion efficiency, then recyclability and non-polluting nature. So about half of all the hydrogen currently produced, it is all obtained from thermocatalytic and gasification processes, since using natural gas as the starting material. So, but there is a large amount of waste which is generated from diverse sources such as food industry, agricultural practices. So all this waste, it can act as a good feedstock for biological hydrogen production. Okay. So biological hydrogen production producers are found to be more environment friendly and less energy intensive compared to thermochemical or electrochemical processes. How? Because in this biological methods, what we use simply, we use bacteria which converts these agricultural and food waste into which helps in the degeneration of these waste, and in the degeneration process they produce different gases, and in that process they can produce hydrogen in since these waste, they consist of high amount of hydrocarbon. So bacteria is used for the uh, generation of hydrogen in this biological processes. Okay. So no external bias is required, nothing is required, only bacteria assist in the production of hydrogen. Okay. So biological hydrogen production processes, basically it is called BHP, from renewable sources such as biomass, water, and organic waste, either biologically or photobiologically. It is called biohydrogen. So the hydrogen which is produced from biological method, it is called biohydrogen. Biological production of hydrogen as a byproduct of microorganism metabolism is an exciting new area of technology. Okay. So BHP at ambient physiological condition is the most obvious and viable approach over energy intensive conventional chemical or electrochemical processes. Okay. A successful biological conversion of biomass to hydrogen depends strongly on the processing of raw material. So it is not like this waste from the food industry and agricultural waste. This is the raw material. We need to prepare a feedstock from it, which can be fermented by the microorganism. It is not like this is the feedstock. That is the raw material. We need to prepare a feedstock which can be easily fermented by the microorganisms to produce hydrogen. Okay. So BHP can be realized by aerobic and photosynthetic microorganisms using hydrocarbon rich and non-toxic raw materials. Okay. So it is classified into different forms. So basically, bio
photolysis, which is direct biophotolysis also there, indirect biophotolysis is also there, then fermentation, photofermentation in the presence of light, dark fermentation in the absence of light, then biological water gas shift reaction, microbial electrolysis cell, and major enzymes. Okay. So the first one is biophotolysis. It is basically the biological hydrogen can be generated from plants by biophotolysis of water using microalgae, that is the green algae and cyanobacter, fermentation of organic compounds and photodecomposition of organic compounds by photosynthetic bacteria. Basically, simply photosynthetic bacteria, there are different types of bacteria which are like green algae, cyanobacter, all these bacteria, they directly takes energy from the sunlight and then split water into its components. Photosynthetic production of hydrogen from water is a biological process that converts sunlight into useful stored chemical energy by following this. Okay. So what happens simply the light energy is absorbed by the pigments at photosystems which raises the energy levels of electrons from water oxidation when they are transferred from like these are the pigments which are available in the feedstock, basically the food waste or agricultural waste. So they absorbs energy from the sun, and bacteria helps absorbs energy from the sun and then gets oxidized using ferredoxin, which is also a bacteria. And this for ferredoxin, it releases electron, which in the presence of hydrogenase converts this water into its components. Okay. Such a reaction with green algae could serve to produce a clean, renewable, and economically viable hydrogen fuel. Since hydrogenase is sensitive to oxygen, green algae is used to maintain. This green algae is used along with the hydrogenase. Hydrogenase helps in the splitting of water, but this green algae is used along with hydrogenase. Why? Because hydrogenase is sensitive to oxygen. So this green algae helps to maintain the oxygen content less than 0.1% so that hydrogen production can be done. Another is indirect biophotolysis. With here, indirect biophotolysis. How? Firstly, what happens is the uh, cyanobacter can also synthesize and evolve hydrogen through photosynthesis. So, firstly, photosynthesis takes place by using carbon dioxide and water to produce glucose. Then, this glucose it reacts with the further moisture or water using light energy to produce uh, hydrogen. So, basically, this is an indirect biophotolysis. How? Because firstly, photosynthesis takes place, which forms carbohydrate, and then this carbohydrate it gets fermented to produce hydrogen. Okay. Now coming on to the fermentation, which is of two type, which is photofermentation and dark fermentation. Photofermentation, basically the fermentation in the presence of light. So photosynthetic bacteria evolved molecular hydrogen catalyzed by nitrogenase under nitrogen deficient conditions using light energy and reduced compounds. So basically, this photosynthesis, after photosynthesis, the glucose gets reduced to hydrogen in the presence of water by using nitrogenase bacteria or nitrogenase enzyme in the presence of light. Okay. Whereas in the dark fermentation, mainly differs from photosynthesis in which it works without the presence of light. Okay. So the dark fermentation employs diverse group of facultative and anaerobic bacteria. Basically, it uses different bacteria such as E. coli, E. cloacae, Clostridium sp for the efficient conversion of wide range of organic substances. For the conversion of these organic substances, such as this glucose gets converted to hydrogen in the absence of light by using different bacteria such as E. coli and E. cloacae. Okay. Then another is biological water gas shift reaction. Hydrogen is produced via water gas shift reaction by photohetero- photoheterotrophic bacteria. So it uses a photoheterotrophic bacteria where while carbon monoxide is oxidized to carbon dioxide in the presence of anaerobic bacteria, hydrogen is released from the water gas shift reaction. Okay. So this carbon monoxide gets converted to carbon dioxide
and hydrogen gas gets released in the water gas shift reaction. Okay. Organisms growing at the expense of this process are the gram negative bacteria. At the during this process there various organism growth takes place, which is some gram negative bacteria grows, which is rhodospirillum rubrum or rubrivax gelatinosus, and gram positive bacteria such as carboxydothermus and hydrogenoformans. Okay. Now, another is the microbial electrolysis cell. So, microbial electrolysis cell is a novel bioelectrochemical tool for hydrogen production that employs domestic and industrial waste as a fuel and uses electrochemically active bacteria. So, here two electrodes are there. This is a separator, and this is the electrochemically active bacteria, which is seen here. So it consists of an anode, a cathode, electrochemically active bacteria, and a power source. Hydrogen production efficiency of microbial electrolysis cell, it is 80 to 100%, significantly higher than that of the dark fermentation process or water electrolysis process. Okay. Coming on to another, which is the major enzyme. So there are various enzymes also which assist in the production of hydrogen. So there are different type of enzymes found in algae and cyanobacter, which is the reversible or classical hydrogenase, membrane-based uptake hydrogenase, or nitrogenase enzymes. So reversible or classical hydrogenase, they oxidize ferrodoxin or other low redox electron carriers, both natural or artificial, and the hydrogen evolution reaction in green algae is due to the reversible hydrogenase. Okay. They're able to take another is the membrane bound uptake hydrogenase. They are able to take up hydrogen at low partial pressure, reducing a relatively high potential electron acceptor, but producing little or no measure. I mean, the amount of hydrogen produced in this section is very less. Okay. Now, third one is the hydrogenase enzyme. They normally reduce nitrogen to ammonia, but can also evolve hydrogen, particularly in the absence of nitrogen. So these enzymes, they produce hydrogen in the absence of nitrogen. So firstly, what they do, they reduce nitrogen to ammonia, which helps them to evolve hydrogen, which helps them to produce hydrogen. Among the algae, only the blue-green algae, that is the cyanobacter, have these enzymes. Okay. So potential hydrogen producing, these are some of the hydrogen producing microorganism. This is the green algae type of microorganism, and this is the name of organism. So these are some of the microorganisms you can see and learn. They may like ask you in the question for matching or something. Okay. And they have different advantages and disadvantages you can study. Now coming on to purification of hydrogen. As you may know that during the production of hydrogen, it comes with the various other mixture of various other gases may also come. That is the carbon dioxide may be there, oxygen may be there, then monoxide may be there. So the gas produced by biological processes mostly contain hydrogen and impurities like carbon dioxide, oxygen, some traces of moisture. So the scrubbers can be used to separate carbon dioxide, which is basically a 50% weight by volume KOH solution, which is a good carbon dioxide absorbent, so it can be used for carbon dioxide absorption. Then alkaline pyrogalol solution is used for the removal of if some traces of oxygen are there in the gas mixture, and if the presence of moisture is there in the gas mixture, then it must be reduced because it will reduce. If the moisture is present, then the heating value of the fuel will be decreased. So all this can be achieved by, so we can remove the moisture either by drying or by chilling. I mean, by drying or by chilling, that is by condensing out the vapor in the form of water. So now coming on to the criteria to choose nanomaterial for biological hydrogen production. It should be photoconductive. Nanomaterial should be photoconductive. Then high catalytic activity should be there. Then non-corrosive should be non-corrosive, and high specific surface area should be there. Okay. Now, coming on to the influence of nanoparticles on biohydrogen production. The use of nanoparticle can be increased significantly for applications such as protein immobilization, biosensors, biofuels, and microbial metabolic activity for hydrogen production. So this is a positive effect on various nanoparticles. There is a positive effect of various nanoparticles such as silver, gold, copper, iron, nickel. On by using this nanoparticle, the efficiency of the biohydrogen production increased. These nanoparticles might be stimulating BHP by their surface and quantum size effect. mean they can improve the biohydrogen production due to their size, quantum size effect, or large surface area, or strong ability to absorb electrons. And the extent of quantum size is directly correlated with the rate of electron transfer between nanoparticles and enzyme molecules. So there are various factors which are involved for selection of a nanoparticles for improving the hydrogen production in any kind of like hydrogen production. It is not like you can introduce a single nanoparticle and you'll all the properties will come with that. Different nanoparticle has different properties, so to improve different nanoparticles you need to sometime introduce more than one type of nanoparticle also. Okay, so coming on to the advantage of this biohydrogen production, effective waste management is there because we are using waste, food waste, agricultural waste, then prevents environmental pollution. Hydrogen can be produced with and without light in few methods. Okay. Need extra efforts to remove impurities like oxygen, carbon dioxide, and moisture. Need more research for bringing this technology from lab to industrial scale. Okay. So it needs more development. It is not still completely developed. Okay. Now coming on to the questions. It would be great if you guys will engage in the question answers. So the first question is the amount of photo generated, sorry, the amount of photo generated current increases slightly with an increase in anyone? You might have seen the answer of this. So let us move to the next one. So the answer to this, with the increase in the temperature, the amount of photo generated current also increases. Moreover, various other factors also increases with the increase of the temperature, such as kinetics and rate of the reaction. All those things increases with the increase in temperature. Okay. Now coming on to what are the two main components of all solar thermal power plants that collect solar energy. Yes, the answer is correct. It is B, that is the reflectors and receivers. Okay. So the two main component for solar thermal power plant, it is the reflectors. Basically, we studied in the last class, reflectors, which are used for, for collecting the, like reflecting the sunlight, taking the sunlight is incidented on the mirrors and then they reflect them to a receiver where the receiver, it absorbs the heat energy from the sun. Okay. So the answer is B. Coming on to the next one, which is in the direct biophotolysis method of hydrogen production, the hydrogenase accepts the electron from to produce hydrogen. The answer is paradoxin. It is correct. I should show you. Here, paradoxin accepts electron. Okay. So the answer is paradoxin. What is the structure of monolayer transition metal dichalcogenides? As the name itself says, dichalcogenide. So two, which is, what did you say? A. Okay. No, A is not the right answer. Let me explain. Dichalcogenides are basically, it is, chalcogenide is two. Basically, two X and one monolayer transition metal, basically. So, one layer of metal sandwiched between two layers of dichalcogenides. Okay. So, the answer is XMX. That is C. Okay. I told you here. Let me show. Here. TMD consists of monolayer stacked. TMD monolayer can be described as a sandwich structure where one layer of transition metal is situated between two layers of chalcogens. Okay. The next question, select the correct relation between carbon and nitrogen with respect to their electronegativity. So, which is more electronegative, carbon or nitrogen?
Nitrogen.
Answer is B. Okay. Yes, the answer is B. Nitrogen is more electronegative compared to carbon. Answer is correct. Black phosphorus is a semiconductor with a crystal structure that is orthorhombic, cubic, hexagonal, amorphous, which is the crystal structure of black phosphorus. Let me see. What are your answers? You guys can speak also. Yeah, the answer is orthorhombic. Let me show you. So this is here we have studied black phosphorus. It is orthorhombic crystal structure. Okay. Coming on to what is the approximate splitting rate of water to hydrogen and oxygen at room temperature?
It is B number. B.
What is the answer?
10 per minus 7. B. B.
Answer is B. Yes, the answer is B. It is 10 to the power, it is very less, 10 to the power minus 7 mole per liter. Let me show you. Yeah, here. So at room temperature, splitting rate of water is very low. It is 10 to the power minus 7 mole per liter. Okay. The answer is B. So in water electrolysis, how is the oxygen evacuated and protons migrate to the cathode? See the options and let me know the answer. In
It
how
is
does the
D.
oxygen is taken out of the system? Yeah. Let me tell you the answer. The oxygen gets circulated through the water circulation. Okay, simply from along with the water, oxygen is circulated out of the system, and proton migrate to the cathode. Okay, let me show. Here, oxygen is evacuated by the water circulation, and proton migrate to the cathode. Okay, basically, I guess there is a mistake. It is PEM water electrolyzer in PEM water electrolyzer. Okay, sorry, it's my mistake. Now match the names of the microorganisms. Basically, uh, you need to like match the microorganisms with the name of the organisms in their I mean similar names. Okay. So the first one is Climadomonas myovusi. So let us see where which option this is. Okay. So here Climadomonas myovusi, it is a green algae. Okay. So it is a green algae. So the its option will be C. Then another is Anabena azole. Anabena azole here. It is a cyanobacteria. So it is a cyanobacteria. So the option A. Then R capsulatus. R capsulatus. So here capsulatus, it is photosynthetic bacteria. So it is a photosynthetic bacteria. It is D. So another next is Aneterobacter aerogenes. So it is simply the option left is fermentative bacteria. Okay. So it is 1C, 2A, 3D, 4B. So the option B is correct. Let me see, did you guys answer? Okay. Option B is correct, Arun. Okay. Now, the last question, what is the band gap criteria for an efficient PEC cell?
It is B number 1.2 electrovolt.
Anyone?
B number B
Let me
1.2
see.
AA.
Did you guys answer? What is the band gap criteria for an efficient PEC cell?
1.2 electrovolt.
Deepak, you're not audible.
It is 1.2 electrovolt EV.
You're
1.2
not
EV.
audible
B
to
number.
me.
Okay, okay.
Please write your answer in the comment. Could you? Yeah, the answer is right. I don't know
Yeah.
why you guys are not audible to me. I guess there is some issue. Okay, I'll look into it. I think there is some problem in my system. Uh, the answer is 2 electron volt, Deepak. Let me show you. We
Okay.
discussed in the slide here the criteria for Good PEC. Okay. So the criteria for choosing a good PEC cell,
It's two.
it should be band
Two.
gap should be 2 electron volt. Okay.
Yeah,
For the
yeah.
nanoparticle, to use a efficient nanoparticle in PC cell, the band gap is one. At least it should be approximately up to 2 electron volt.
Mm,
Okay.
right.
So that's all for today. I guess I took a lot of time. I hope I was clear. And if you guys have any questions, you may ask. Deepak, you're not audible. Can you please write your question?
Hello.
Hello, Deepak.
Ah, ah, now I am audible.
If you're trying to say something, please type it because you're not audible to me. And if there are no issues, then we may end today's class and we'll meet day after tomorrow. Um, yeah, type, Arun, may type your query, please. Okay. Actually, that procedure for final exam, I can ask from the professor only because he'll be the one preparing. I also did not give NPTEL exams anytime before. I'm just a tutorial, like I'm taking the tutorials, but I can definitely ask this question for you. Okay, let me just note it down. I'll ask the procedure of for final exams for you. Okay, that will be fine. I'll try to answer this question by the next class. Will that be fine? I, as much as I know, it will be MCQ most probably. Apart from that, I will definitely confirm it with the professor, Professor Kaushik Pal, and I'll let you know. Will that be fine, Arun? Okay. Okay, then see you day after tomorrow. I hope you guys will join. Okay. Chalo. Thank you. I'll upload this presentation as well as the video online. Then you can refer it for the future purpose. Okay. Okay. Thank you, guys. Thank you.